Hey, welcome back to our continuing discussion of antiderivatives. If you've never liked derivatives before, again, this is your lesson. So we are going ahead and warm up and just solve a couple of integrals. Now, we'll come back to this one just a little bit, but I do want to take a look at number 2. Mainly, I want to look at all the parts of an integral itself. Remember the little symbol here? We call this an integrand. And an integrand is an operator. Kind of like addition and subtraction. It's telling me to solve a derivative. That's what this is telling us to do. To solve a derivative. The dx right here, remember we call that is the differential. And what that is telling us is everything inside of our integral is a derivative. So we want to solve this. We want to solve this derivative equation. In other words, we want to bring the function back. Yeah. Remember the good news? There is no product rule. So we're going to distribute here. Pretty easy to do. And I'm only distributing, so this becomes, of course, cosecant x, cotangent x, minus cosecant squared of x. Now, I'm only distributing. I have not taken the antiderivative yet, so I'm still going to have my differential, and I'm still going to have my integrand. But now I can solve this. Ready? In our list, we're looking for the function whose derivative is cosecant cotangent, and hopefully we should remember that is negative cosecant of x, minus, and now we're looking for which function's derivative is cosecant squared. Well, we should know that that is negative cotangent. And of course, two negatives make a positive, so I can write this as positive cotangent of x. Don't forget the child. Don't forget that C1 right there. Right, there we go. Right. Recall from yesterday, we call these indefinite integrals. In other words, we don't know what the value of c is. C is unknown. And that is why we call them indefinite. It can be anything. To help solve for c, we use something called solving differential equations. And remember, anytime we see the word differential, that is a key word for the word derivative. So we want to solve a derivative. In other words, how do we find c? That's our goal. How do we find the c value? To solve a differential equation, well, remember we saw an example like this yesterday. A derivative equation or differential equation is something that says the derivative is equal to the slope of a function. And our ultimate goal here is to solve for y. So like in Algebra 1, if I want to get y by itself, I have to isolate it. So I'm going to multiply it by the dx part on both sides. And this becomes dy equals f prime of x dx. Now remember, this is saying that this is a derivative, so now we have to undo the derivative. Well, this is not like an algebra problem. We have to do the inverse of a derivative. And to do that, we use antiderivatives. We have a special symbol to represent we're taking an antiderivative. And that's why we call this an operator up here. This integrand sign is an operator. It's telling me I want to find the antiderivative of both sides. Golden rule of math. What you do for one side, you do to the other. Now, when we take the antiderivative, recall from yesterday, we also said that the antiderivative, the integral, and f prime are inverses. So they cancel each other out. So it's kind of like this. If this integral cancels with that prime, and what we're left with is just f of x, but we had an original constant, we didn't know what it was, so we go plus c1, and of course the antiderivative of y, remember there's a 1 there, that's just y. And today, we are going to solve for C1. Now remember, this is not a derivative. This is the function itself. So let's talk about C real quick. Because C can represent any number, it is actually impossible to know for sure what C is. For example, if we have y prime of x equals 1, by taking the antiderivative, we get the line y equals x plus C1. This is a line. However, since C can represent any number, we can never be for certain what the y-intercept is. So in other words, since we can never be certain, we say this is not unique. So, because there can be infinitely many of them. I mean, I can draw a bunch of them. Here is just y equals x minus 1, y equals x plus 1. And we can have infinitely many lines as for whatever C can be. Differential equations allow us to solve for C given a certain initial condition. So let's say we're given the following derivative. We want to find the equation for y. So what they're saying to do here is to solve this differential. Given y of 0 is 1. So they give us some initial condition. So when solving it, the first thing I'm going to do is, since I'm solving for y, I have to bring my x's to one side. X's to one side. And to do that, we would get dy equals 8x cubed plus 3x squared dx. First step in solving. All my x's are together, all my y's are together. Never have your x's and your y's mixed up. I promise you, it's not fun. Did that at my wedding. Terrible. Alright, so next, we're going to integrate, because now I want to undo that derivative. And of course, this is just a 1 here, so that just becomes y. Now it's really y plus c1. So let's take a look here. I'm really getting y plus c1. But on the other side, remember, I'm getting some function, f of x plus another constant. When you integrate, well, I can combine those two, and that becomes just another constant. Because these are constant, I can absorb them into each other and make another constant. So we typically only write the one constant versus the two. And that's what we do here. So we don't typically put the constant on the right side, the left side of the equation. We typically put it on the left side. All right. Using our power rule, this becomes x to the fourth over 4, if I'm multiplying that by 8, so it becomes 2x to the fourth, plus this becomes 3x cubed over 3, or just x cubed plus c1. This is our indefinite integral. Remember, what that means is this is not unique because of that constant. So what we're going to do next, and show you work on this, let the AP know, find that constant. We're going to use the initial condition, the x point 0, 1. There's my initial condition as a point, and I can plug that in. When x is 0, y is 1. I can plug that in. 1 equals 0 plus c1. So therefore c1 is 1. Now I can write my unique equation. Even though this is not unique, there's only one that goes through that point. So we would get y equals 2x to the fourth plus x cubed plus 1. And there is our new function. This is unique. And that is because we are given a condition. At this point, this is what we want. So let's try another one together. Find the equation for y if the second derivative is sine plus cosine and given the following initial conditions. Notice they're giving us the initial value and the initial derivative. We had a problem like this yesterday. So if they give me the second derivative, I must first find the first derivative. And I can do that pretty quickly. Let's just use y prime since they're using primes. Y prime equals the antiderivative of my second derivative. Remember, if I want to find my first derivative, I have to undo my second derivative. And we do that by using integrals. Plus cosine theta. Be careful, d theta. Don't forget the differential. They're not going to remind you about it. You just have to put it. And we're using theta this time. If you use x, the AP will be okay with that. They'll be, oh, look, they can't spell theta right. So when we integrate this one, well, sine's antiderivative, be careful, what function's derivative is sine? Is negative cosine theta. What function's derivative of cosine is sine theta plus C1. So now we have to find C1. And I'm going to use the initial condition, but use the right one. Remember, sorry, that was y prime. Use the correct one. We know y prime of 0 is 4. And I can just plug it all in. 4 equals negative. Cosine of 0 is just 1. You should be able to do that in your head. Sine of 0 is 0 plus C1, so C1 is 5. So our derivative is negative cosine theta plus sine theta plus 5. So there's our first part. But now, remember, we want to find the original y value, so now we have to find y. Well, y, to get the original function, we have to undo our derivative. So we're going to use antiderivative, negative cosine theta plus sine theta plus 5 d theta. Be careful, theta's always confuse people. And when we do this one, we would get y equals, be careful, the antiderivative cosine is sine, so this is just negative sine theta. The antiderivative of sine is negative cosine theta plus, now be careful with the 5, you need to put a variable there, plus theta. Don't put an x, be very careful. If you want to use x, make everything an x. Don't also make theta theta x, it'll mess you up. Plus, now we've already used C1, so I'm going to use C2. So now we have to find C2, and they give us the initial condition, y of 0 equals 4. I can just plug it in. So we would get 4 equals sine of 0 is 0 minus cosine of 0 is 1 plus 5 times 0 is 0 plus C2. So therefore C2 is also 5. And my final answer, oh no, I ran out of room here. Let me see if I can squeeze it in. Y equals negative sine theta minus cosine theta plus 5 theta plus 5. And there is our function. All right, hope you enjoyed this part. Go to part 2. We'll take a look at a bunch more examples.